Hi everybody, let's continue talking about the brain. This video will be a little bit longer because I have two videos incorporated into it, and as always, in case YouTube cuts it, I will show you how to find the link so you can watch them yourself. So we went over the overview of the brain and the different areas, and now we're going to start diving in and looking at how it looks and looking at the specific areas and what they do. But we're going to start with the external anatomy. And part of it is naming different areas and just a general description of why it looks the way it does. Now what you're looking at here, all this squiggly bit, this is the cortex. Cortex means bark, so that's going to be the outside. And the cortex is the outermost part of the cerebrum. It's the largest part of the brain, about 40% of total brain mass. And it's all folded. It's all these are folds. And anytime you have folds in something, pretty much it's to increase your surface area. 2/3 of the surface is actually hidden down inside the grooves. And so all these folds increase the surface area about 3 times what it would normally be. And the more you use it, the more folding you have. So a fetus's brain is smooth until it starts to fold. And we actually have seen people in long-term comas, like many years after they pass. If they dissect the brain, they can see some of the folds have smoothed out because you're not making those connections. So folding will increase the surface area. And everybody has unique folding in their brain. It looks like the differences in the way my brain folds, the way your brain folds, is even more unique, although unique doesn't get a modifier. It's I'm stuck here because you can't say more unique. You know, unique is unique, but so I'm going to do it anyway. It's more unique than fingerprints. So every person has different folding in their brain, and the folding isn't random. Because the way your nerve networks form affects the folding. So if you use different parts of the brain, that's going to form connections, and that changes the way your brain folds. So it's not like we just randomly crunkled up the brain like crumbling a piece of paper. It's very specific for each person and for what they learn throughout their lives. But we have seen some differences. So, well, premature infants, because the folding begins during fetal period at about 6 months or so. So when you're a premature infant, there's not as much folding in the brain. And the brain actually is a little smaller than full-term newborns. With autism has increased folding compared to neurotypical. And so there's increased surface area and bigger brains. Depression, it's abnormalities in the folding. It looks like some parts of the occipital lobe back here can fold over themselves. I don't know if that causes depression, if depression causes the folding, or if it's due to some third factor. We don't know. Now, schizophrenia, overall there's less folding, and there's different folding patterns in Broca's area. Broca's area is the motor speech cortex and in the frontal lobes. So the folding is complex and unique and important. Now, we name different parts based on how they look. The elevated ridges, this is a gyrus, a gyri is the plural. So these elevated ridges, this one, okay, let me give you this line here in red is a sulcus. That's an invagination, that's a depression. This line right here is called the central sulcus. It separates the frontal lobe from the parietal lobe. This gyrus, this elevated ridge of tissue in front of the central sulcus, is called the precentral gyrus. That is the primary motor area. That's where you're going to start voluntary movement. This area behind the central sulcus in the parietal lobe is called the postcentral gyrus. That's the primary somatosensory area. That's where sensation of touch goes. And one more gyrus, this one you have to look inside, the cingulate gyrus. Cingulate gyrus is right here, and it's important in memory, empathy, OCD, motivation, problem solving, a whole bunch of different things, but social worrying too. How do I stack up against other people? You find that mostly in the anterior part. All right, so the gyri are the elevated ridges. I will want you to know pre-central gyrus and post-central gyrus. All right, the sulci. A single one is called a sulcus. That's a groove or a furrow. And the central sulcus separates the frontal lobe from the parietal lobe. And everyone's look different. Every brain is going to look different, but it's always right around here. Now the lateral sulcus, that's going to separate the temporal lobe from the frontal and parietal lobe and all the other lobes. All right. Fissures. Fissures are going to be deeper invaginations. The longitudinal fissure, that separates the left and right hemispheres, and the transverse fissure is going to separate the cerebellum from the cerebrum. I'm going to pause for a moment to talk about phrenology. Phrenology was very popular in the 19th century, so in the 1800s, early 1800s. And basically what they thought was you could feel somebody's skull and figure out what kind of personality they had based on that. They thought that the propensity for certain personality traits was related to the dimensions of your head, because they thought it was in your brain. Okay, good. So maybe different personality traits are in your head, but somehow they thought that would change the way your skull feels. Don't worry about Florins and Gall. I won't ask specifically about them. But they reduced intelligence personality to 42 separate functions. So are you a thief? Are you intelligent? Are you selfish? Are you loving? All these different things. And they decided they were all located in different parts of the brain. So if you had a lump here, then you had good parental love. or if you had different things, and they'd feel your skull and make assumptions about your personality based on lumps and bumps of your skull. And it was very much a circular argument. Pretty much they'd say, okay, he's a thief because he has a bump over the acquisitiveness area. Well, how do you know that bump there means, how do you know that's the acquisitiveness area? Well, because he's a thief and he has a bump there. So it had no scientific merit whatsoever. But it really made a difference in that sometimes you couldn't get a job, and they would make you take a phrenology test, and they'd feel your skull and they'd say, oh, you have a bump here, we can't hire you, you're a thief. Maybe you just bumped your head. Or you couldn't get married to somebody if they hired somebody to do a phrenology test. So it really mattered for a while there. But it's not science. They had all these circular arguments and they didn't prove it. But it did encourage further study. It said that maybe our personality is in the brain. Now, one interesting thing, a couple years ago, back in 2017, some researchers scientifically tested phrenology. They got MRI scans of about 5,700 people's skulls, and they correlated it with the behavior. And they found no correlation. So 200 years later, they disproved this theory. All right, looking more at the anatomy. We talk about gray matter and white matter. Now, what is the difference between gray matter and white matter? Gray matter is the cell bodies, the dendrites, sometimes the axon terminals, the synapse, and some glia. Okay, leaving pretty much, let me put this up here. The white matter is the axons. All right, so here is gray matter. You can see it looks slightly different, but here's the axons of fibers look more white. And most of the cerebrum actually is the fibers, is the axons. And the axons look white because they are myelinated. And that's that fatty protein substance. So it actually physically looks white. And that's going to be the connections. But the gray matter is going to be the cell bodies and the dendrites and the synapses and some glial too. And in the brain, the gray matter is going to be on the outside, closer to the surface. And then the fibers lead in and down to your spinal cord. So we're going to talk about different connections between areas of the brain and ways that fibers connect. So commissures, these are fibers that connect the two hemispheres. And the main one you need to know is called the corpus callosum. So learn that name. And what the corpus callosum is there's a huge system of fibers that cross from the left to the right hemisphere. And I'll come back to this and talk about what happens when you sever it. It's because it's really cool. But it's connects the two hemispheres, and it's important in sending tasks back and forth. My neuroanatomy professor from grad school is one of the guys who dissected Einstein's brain. He was a real, I think he's still alive. He's like 90 something. He's a cool guy. Not Einstein. Einstein was cool too, but my anatomy professor. And one of the things he found is that Einstein had a thicker corpus callosum. We don't know how to correlate that with what it means. It's an N of 1, but it's interesting. The anterior commissure connects the olfactory cortices, the cortexes in the two hemispheres. And one interesting thing, this is bigger in gay men than it is in straight men. It's the biggest in gay men, and then in straight women, and then in straight men. And they didn't measure it in lesbians because there's the least research done on bisexual and gay women. Of course, most of orientation research is done on gay men. But anyway, it's bigger in gay men. Association fibers. Those are going to be fibers that transmit signals within one hemisphere. So it's only on the left or it's only on the right. And one we'll talk about later in the semester is called the fornix. And that connects the hippocampus with the hypothalamus. And finally, there are projection fibers. That connects the cortex to the rest of the central nervous system and to the body. So one of them, for instance, is called the internal capsule. That carries signals through the thalamus, and it's a pathway just to the brain and to the rest of the brain and spinal cord. All right. So here we are in the telencephalon. And remember, the telencephalon is in the forebrain, and it's made up of the left and right hemisphere, and it involves the cortex, which has actually 5 lobes. So frontal, parietal, temporal, occipital, and insulas underneath. We'll talk about those in the next video. And the basal ganglia, those are all in the telencephalon. So for now and for the next few lectures, we're going to be talking about the telencephalon. Looking at the hemispheres, we got the left brain and the right brain. And here is that corpus callosum, these big series of fibers, 300 million fibers that connect the left and right hemispheres. Now, this is not the only thing that connects the two halves of the brain. Some information crosses the other side of the brain by other pathways. So we're going to talk about experiments where they severed the corpus callosum. It's not like chopping an axe through the entire brain. It's just severing some connections between the left and right hemisphere. There are still some information that can pass from left to right. And our hemispheres are contralateral. So left hemisphere largely controls the right side of the body, and vice versa. Now, people often talk about being left brain or right brained. So what are the differences between the left and right hemispheres? And I will tell you that people greatly overestimate what that means. Unless you're missing half a brain, we're all use left and right hemisphere. So we may be more dominant on one side, and many are left dominant hemisphere because most of us are right-handed. But it's not as clear cut as those, BuzzFeed tests or quizzes you take that just say, oh, you did this, you're left-brained. Well, it's not as clear cut. We say that language is on the left hemisphere, and to a large degree that's correct, but it's not all of language. So what we see in the left hemisphere is speech and writing and reading, verbal and computational skills, music in trained musicians. Music in non-musicians is more on the right hemisphere. So just the appreciation, the emotional connection. But if you're a trained musician, it's a math thing, it's language. I'm a musician. You read the score, that's a language that you've learned that little black dot, on this corresponds to a certain note and a certain way to play it and all of that. So it's a language in trained musicians. Other things about language, the time of the left hemisphere, is time and details, order, rules, deadlines. That's more left hemisphere. And simple language. So putting words together in the proper order. That's going to be more the language of the left hemisphere. All right. But having the nuance and complexity of language and the music of language, that's going to be more right hemisphere. But big picture, language is speech, writing, reading, verbal, time, details, order, rules. Right hemisphere is much fluffier. It's putting all these elements together as a whole. It's more creative. It's spatial perception and art, music, emotions, intuition, recognizing faces seems to be more right hemisphere. The ability to tell if somebody's lying or sarcastic or joking. So the words they are saying, that can be comprehended on the left hemisphere, but you can see how important it is to tell if somebody is, the words may be saying one thing, but you can tell if they're sarcastic based on their inflections, based on the word order, their expressions, all those things go into it. So that's more right hemisphere. And right hemisphere is more the intonation you put into your tone. Like, how do you feel? Like, I'm fine. You know, if you only had left hemisphere, you'd hear I'm fine and think, oh, great, she's fine. But beware, because I'm not. So hearing that emotional tone and getting the complexity from it, that's going to be more right hemisphere. And there is a gender difference in that men tend to be more lateralized. Men do tend to be more left brain or right brain. Women, females tend, so I should say females because it's a sex thing, not a gender thing. So females tend to be able to use both sides of the brain and pull things back and forth more than males do. Here's an example in that when males have a stroke on the left brain, they are 3 times as more likely to lose the ability to speak. Females who have a stroke in the language center and the left brain are much more likely to be able to get speech back. They can pull in the other hemisphere more. So we do see differences in males tend to be a little more lateralized. And, you know, I teach human sexuality. Men tend to be more gay or straight. We see less bisexuality in men. In women, women are more likely to be bisexual. It's like, now I like men, now I like women, now I like everybody, hooray. We see that more in women for a variety of reasons. If you want to take human sexuality with me, great. But I always think of this. So it's like men tend to be more focused. There's your left brain or right brain, and females are more, all right, let's use it all. Now let's get into some of the videos. Roger Sperry, who actually went to my high school many, many years before I did, but he won the Nobel Prize because what he did is he cut the corpus callosum in patients with severe epilepsy. And he got the Nobel Prize for this in '81. And why he did this, with severe epilepsy, there's different forms of seizures. And when the seizure crosses from one hemisphere to the other hemisphere, that's when you lose consciousness. And that's the dangers. That's tonic-clonic, used to be called a grand mal seizure. But there are patients with severe epilepsy who can have dozens of seizures a day. And you're losing oxygen and you can't survive. And these patients who, I mean, they have no value of life. No, I'm sorry, I shouldn't say value at all. I meant quality of life. And so some of these patients weren't responding to drugs. This is before they were giving CBD. And so the only treatment he did is he cut the corpus callosum so that signal, that seizure, wouldn't cross to the other hemisphere so they didn't lose consciousness. And so we had a bunch of people who had the corpus callosum cut. And what happens is, since the brain is contralateral, but we've cut a large part of the thing that sends signals from one side to the other, what he would do is he'd have these patients stare straight ahead. He'd shine an image on a split screen, and the image seen by the left eye goes to the right brain, and the image seen by the right eye goes to the left brain because it's contralateral. So these patients would be staring straight ahead, all right, and wouldn't see what's over here. And so spoon, if you see the word spoon, it's on the right visual field, it goes to the left brain. If you ask the patient, what did you see? He can say, I saw spoon, because this image is going to the left brain. But if you show the image to the right brain and ask them, what did you see? They couldn't say it because simple speech was here in the left. They say, oh, I didn't see anything, or I don't know, or whatever. They couldn't say that word that was going to the right brain. Nope, didn't see anything, I don't know. But what he then had them do is he'd have them with their left hand feel a whole bunch of objects and say, what did you see? They could, by feel, pick up the object. They couldn't say it, but their spoon went to their right brain. Right brain controls the left hand, so their left hand knew to pick up spoon, even though they couldn't say spoon. So let me show you a video of people who had this done. Okay.
I know the left hemisphere and right hemisphere now are working independent of each other, but you don't notice it. Now you just kind of adapt to it. It doesn't, you don't have any feeling, it doesn't feel any different than it did before.
7 years ago, Joe had brain surgery to allay the effects of severe epilepsy. His surgeon cut the nerve fibers connecting his left hemisphere with his right. While the operation was a complete success, Joe's unusual case offers an extraordinary insight into the machinery of mind.
So it hasn't really made any.
This fiber system, the corpus callosum, is located midway between the two hemispheres. When it was surgically severed in Joe's brain, the transmission of information between the two hemispheres was halted. Michael Gazzaniga.
What we can do is play tricks by putting information into his disconnected, mute, non-talking right hemisphere and watch it produce behaviors. And out of that, we can really see that there is, in fact, a reason to believe that there's all kinds of complex processes going on outside of his conscious awareness of his left half brain. Joe, I'm going to show you some things. I just want you to tell me what you see. And here we go. You ready? Look right at the dot. Okay, right. Okay, you ready? Look right at the dot.
Grapes.
Good. When Joe focuses on a point, right at the dot, everything to the right of the point goes to his left brain, the dominant hemisphere for language and speech.
Look right at the dot.
So we can see here that when we flash a word or a picture, Joe is easily able to name it. Here we go.
See it.
Close your eyes and let your left hand do a little work here. Okay, what do you got there?
Pan.
Okay, very good. Now, when a word or a picture falls to the left of a fixation point, that information goes to his disconnected right half brain. And as we can see here, Joe is unable to name it. Joe is able to draw the picture with his left hand, the left hand getting its major control from the right half brain. What did you draw?
Okay.
What did you see?
Wheel on one side. I don't know what I saw in there.
So even though he can't name it, his left hand is able to draw out the picture of the stimulus of the picture or word that we presented to his right half brain. What did you see?
So, hammer.
So just close your eyes and draw with your left hand. Just let it go. It's nice. What's that?
Saw.
Yeah. What'd you see?
Hammer.
What'd you draw that for?
I don't know.
What we have with Joe is just a dramatic example of a neurologic case that really allows you this window into the non-conscious and how powerful non-conscious processes are at influencing our conscious self, our personal self. What Joe and patients like him, and there are many of them, teaches us is that the mind is made up of a constellation of independent, semi-independent agents, and that these agents, these processes can carry on a vast number of activities outside of our conscious awareness. Even though that goes on, there's some final stage or some final system, which I happen to think is in the left hemisphere, that pulls all of this information together into a theory. It has to generate a theory to explain all of this all of these independent elements. And so, and that theory becomes our particular theory of ourself and of the world.
Okay, so just so you have it, I'm just going to click on this again. Well, I'll give you the address in case YouTube makes me cut it out. So some things can cross the other side versus via other pathways. So emotions can cross, the language couldn't cross. And one neat thing we see with the emotions able to cross, they did this with a teenage boy who had to have his corpus callosum severed. They showed him a picture of his girlfriend to his right brain. All right, so it went to his right brain, and they said, "What did you see?" And he said he saw nothing because that's not the speech center, but he blushed and he giggled. So there was a signal that got there. Emotions can cross. They asked the kid what he wanted to do when he grew up, and he said a draftsman, which is like being an architect, and his left hand spelled out race car driver. So emotions can cross, and they can give you sometimes different answers from what you're actually saying. Now here's an image. If you were to stare at the dot, all right, the image of the woman's face goes to your right brain because it crosses. The image of the man's face goes to your left brain. So if you ask a person to say what they saw, they'll say man, which is going to the verbal centers on your left brain. If you ask them to point out a picture or to draw, so point out a picture of what they saw, they'll pick out the face of a woman because it's going to the right brain and face recognition is on the right. All right, I just find this all cool. Now, the last thing I'm just going to show, and it's going to be, as I said, a long video, it already is one other cool thing with information, getting different information to the left brain and the right brain. Alien hand syndrome. So let me pull this in. So if they make me cut it, you can search on NPR, and it's called Invisibilia, the otherworldly alien hand syndrome. And so you can search for this video if you like, but hopefully we can keep it here on YouTube.
Geico's been helping people save money for over 75 years.
This very serious operation on her brain. The operation was to treat Karen's epilepsy. So her doctors put her to sleep and cut into her brain. And Karen says when she woke up, her speech was a little funny, but basically she felt great.
I had woken up and I was sitting on the hospital bed talking to my surgeon, and
then all of a sudden, her left hand picked itself up and started moving towards her shirt, started delicately undoing its pearly top button.
my hand was taking my clothes off.
Taking your clothes off?
Yeah, my hand was taking my shirt off. The surgeon was like, "Karen, do you realize what's happening?"
And then, all of a sudden, the hand seemed to get angry.
It was tearing the buttons off the shirt.
Karen kept telling it to stop.
Knock it off, knock it off, knock it off.
Her surgeon was screaming at her to control it.
Try to make it stop. I said, "I can't, I won't stop it." And then I started to cry. I just didn't know what to do.
When Karen went home from the hospital, the hand, this new hand with a mind of its own, went with her. A lot of the time, the hand was okay. But it would also get really upset with her. Like sometimes, when Karen did something it didn't like,
Smacked me right across my face.
your own hand. Her problem, the doctors explained, was alien hand syndrome. See, to cure her epilepsy, they'd had to sever the two halves of her brain. So, without her corpus callosum, her right hand seemed to be getting directions primarily from her left hemisphere, and her left hand, this new alien hand, seemed to be getting directions primarily from her right hemisphere.
Half my brain just didn't particularly care for me too much.
Now, this is not science. It's just how Karen sees it. She says she thinks her hand wants her to be more moral. Take, for example, what her alien hand does when she tries to smoke.
When I go to light a cigarette, the hand will either put the cigarette out or flip the ashes around.
And though she's learned to live with it, she's in her 50s now. She's not always happy with it.
I understand that you want me to quit, but cut the crap.
Hannah Rosen, NPR News.